Okay, today we're going to look more deeply at permutations. So, as previously said, a permutation is the way of finding how many possible ways there is of arranging different objects. So it's how many ways there are of arranging objects or digits. For example, say we had 5 and 9, then there's two ways of arranging them. You can either have 59 or 95. There's different ways of working out the permutations of a set, but they all involve the factorial function. So let's say we had, so the number of permutations of n distinct objects is denoted by this notation, n, p for permutation, n. And the number of permutations is just n factorial for any number greater, for n greater than 0. So in our example up here, n equals 2, so we'd have 2, permutation of 2 is going to be 2 factorial, which is 2. Let's consider the digits 5, 6 and 7 and how many possible 3-digit numbers we can make from those. So you could just sit down and try and work through them. A way of doing that would be using a tree diagram. So if the left hand digit is, like the hundreds column is 5 to begin with, then the middle could be either 6 or 7, and then the right hand digit would be 7 or 6. So then you'd have 5, 6, 7, and 5, 7, 6. If you had 6 as your left hand digit, and then you'd have 5 and 7 as the possible 2 for the middle digit, then you'd have either 7 or 5 for the right digit. So that would then, the next combinations would be 6, 5, 7, 6, 7, 5. And finally, if you had 7 as the left hand digit, you would then have 5 or 6, and then 6 or 5. So you'd have 7, 5, 6, or 7, 6, 5. So there's 1, 2, 3, 4, 5, 6 combinations. Now, this is a bit tedious with just 3 digits, and it becomes a lot more tedious when you get larger numbers of digits. So by doing the factorial method, for this one you'd have 3p, which is 3 factorial, which is 3 times 2 times 1, which is 6, which is what we got. It's a lot quicker. And if you had, for example, a combination of letters and numbers, and you wanted to find all the different combinations that you would have with a combination of letters and numbers that had where n was, say, 5,000, well, doing this tree branch method is just completely and utterly not practical. Even if if n was equal to 7, then we would have 7 factorial would be 5,040 different ways of arranging 7 objects. So you see with the and as you've seen previously with factorial functions, the numbers get big very, very quickly. So let's just look at a couple of the examples. In how many different ways can 5 boys be arranged in a row? So that's going to be permutations of with n equals 5, it's 5 factorial, which will be 5 times 4 times 3 times 2 times 1, which is 120 ways. And how many ways can 9 mice, or 9 elephants, and 4 mice be arranged in a line? Now, how many objects? So we've got 9 elephants and 4 mice, but how many objects do we have altogether? We have 13, because 9 add 4 is 13. So we have 13, n's 13, and so it's going to be 13 factorial, which is a massive number. 6, 2, 2, 7, 0, 2, 0, 8, 0, 0 ways. Typically though, large numbers should be given to 3 significant figures. Unless otherwise stated. So I hope that